Okay, so for the next couple days, we're going to be talking about what we call concentration. Basically, it's how much stuff is dissolved into a solution per how much volume you have. All right, so if we're using an acid in a lab, and I say that something has a molar concentration of 4 and something else has a molar concentration of 2, you'll know that this one has twice as much stuff dissolved into it because its concentration is twice as high, which means that this would be more potent, and you definitely don't want to get that on yourself. Okay, so before we go into that though, let's define some vocabulary. All right, so solution, whenever I'm talking about that, really just means a mixture that is a homogeneous one. Okay, so a solution is a homogeneous mixture. Okay, and a homogeneous mixture is a solution. I'm kidding. That would be stupid to define each one with just the other word. A homogeneous mixture means that when you mix two things together, you can't see the difference between the pieces. Okay, so if you think about like, I don't know, mixing food coloring and water. All right, after it's all mixed together, you can't tell what part of it was the food coloring originally and what part was the water. All right, it is an even mix. It looks different than it did before you mixed the two, but you can't see individual pieces. You can't identify, well, this is substance A and this is substance B. Another example of this would be like brass. Right? Brass is a combination of copper and tin. You can't see individual bits of copper and tin. You see one single thing, brass. Okay, so a homogeneous mixture is a mixture where the individual parts are indistinguishable. We can't tell the separate ingredients apart from each other. Like a cake, that would be a homogeneous mixture. Okay? A heterogeneous mixture, so part of this, you can actually see it in the root words. Homo means same. Hetero means different. Okay? So heterogeneous, well, that means that you'll be able to see the difference between the parts. All right? If you're mixing like gravel and water, you can try and mix them together, but they will separate back out. Oil and water, a heterogeneous mixture. Skittles, you've got a heterogeneous mixture of colors and flavors. All right, you can still tell the difference between them, but they are mixed together. Okay, so a mixture. There we go. A mixture where the parts are distinguishable. So we can tell the difference between the pieces. All right? So when we're looking at a solution, typically it will be formed by something being dissolved into something else. Okay? In most cases, we'll be looking at acids or things being dissolved into water. Okay? So whenever something is being put together into a solution, something will be dissolving and something else will be doing the dissolving. Okay? So those are our two pieces. We've got a solvent and a solute. A solvent is the chemical that is doing the dissolving. Okay? And the solute, well, that's the chemical that is being dissolved. Okay, so if we're looking at making salt water, all right, you're putting solid salt into a solution of water. At the end, the salt will have dissolved in, and the water will still be there. Okay, so the solvent in that case will be water, and the solute would be the salt. Okay, the solvent in pretty much anything we're making a solution is going to be water. Water is an amazing solvent, just based on the shape of it. It's a polar molecule. The hydrogens still stay mostly positive. The oxygen becomes kind of negative because of how the electrons are moving around and how their shells are actually structured. Okay, so because it's what we call a polar molecule, or one side's positive and one side's negative, it's very good at ripping things apart, attracting ions off of stuff and dissolving things down. Okay, so when we're looking at a solution, most of the time we're going to be looking at an aqueous solution. This is a solution where the solvent is water. Solution, not solution, where the solvent is water. Give water enough time and it'll basically break through anything. That's why things that are insoluble in water are so rare, like oil. That's obnoxious. Most things we can tear apart using water. When you're cleaning things, the main portion, or the main solvent there, that's actually tearing apart any grease or dirt, it's the water. All right, so it's a very good solvent. Most of the time when we're talking about solutions, they will be aqueous solutions. So aqui has aqua in there. It's talking about water. Solutions made from water. All right, solubility. So when you're looking at how easily something dissolves, all right, you give it enough time. Water can dissolve dirt and rock, all right, carve out a Grand Canyon, okay, compared to dissolving salt. Way easier to dissolve salt down because salt is more soluble. Solubility describes how easily something can be dissolved. The more soluble something is, the more easily it will dissolve. Water solubility is all of that, how easily something can be dissolved, but specifically in water. Most of the time when we're talking about solubility, we're talking about water solubility because water will usually be our solvent. Okay? We got some more vocab, but I need to clear some space on the board, so I'm going to pause it right now. So the next thing on there is solubility curve. Now this big ugly graph is expressing solubility curve. So let's look at what's actually on here. So over on the left-hand side, grams of solute per 100 grams of water. Okay, so the solute, that's the thing that's getting dissolved. And if we look at the lines, each one of these represents a different chemical. Like NaCl, this line right here is salt. All right, KCl, this is potassium chloride, a different ionic compound. And we've got potassium nitrate, sodium nitrate, potassium iodide, ammonia is this one that's going down, kind of a weird one amongst them. All right, so as a general trend, most of the time when you're dissolving stuff into water, the warmer it is, the more you'll be able to dissolve in. All right, so if you think about what's happening as something heats up, okay, heat is really just a representation of how quickly atoms are moving around. So if it's got more heat energy in the water, it should be able to break apart molecules more easily. All right? There are some oddities, like ammonia, where you can actually dissolve less ammonia the warmer that it gets. Okay? Also notice this thing only goes from 0 to 100. There's a very specific reason for that. Can't dissolve something into water if it's frozen, and you can't dissolve something into water if it's a gas. Okay? So we're looking specifically at stuff that is being dissolved into liquid water. All right? So let's look at sodium chloride. All right? So that line right there. You can see that at 0 degrees, so right at the point of freezing, you can get, I don't know, probably about like 37 grams of salt dissolved into 100 milliliters of water. All right? But as it heats up, as it gets up to boiling, you can get about 40 in there. So there isn't a very significant change as far as salt is concerned, but if we look at something like potassium chloride, all right, when the water is nearly frozen, you can probably get about 28 grams of potassium chloride in there, actually dissolving down properly. But once it's heated up to near boiling, you can get up to 55 grams. All right, so individual chemicals will change how much they can be dissolved into water or whatever your solute is, dependent on your temperature. And most of the time, as you increase the temperature, you'll increase how much will be able to dissolve into the solution. Okay? We may have time for a lab on that. Maybe. The next two things that I want to look at are dilute solutions and saturated solutions. So both of these are solutions. You still won't be able to tell the difference between the individual parts that are trying to be mixed together. Okay? With a dilute solution, this is mostly water. Okay, just a little sprinkling of something in there. It's almost entirely water. It will mostly behave as water, at the same density as water, same boiling point. It's mostly water. And for all intents and purposes, when you're actually calculating stuff, it's water. All right, the more diluted it is, the closer it will be to behaving like water. All right, a saturated solution means that it is just barely able to dissolve. Okay, has the maximum amount of material dissolved into it. Okay, so if you think about salt and water, all right, you pour salt in, it dissolves into water. But if you pour a whole bag of salt in, you'll eventually reach a point where that salt won't dissolve. There just isn't enough water to actually break down all of those salt crystals. Okay, so a saturated solution is right before that. Right, there's a certain point where if you're putting salt into water, it will still dissolve, and if you go just a little bit over that, there's too much salt for the water to break down, and you'll just be left with a solid piece of salt and water. Okay, so a saturated solution is that maximum amount before it doesn't dissolve anymore. Okay, and that's actually what was being expressed on that solubility curve. Okay, the amount that it had, the amount in grams, that was how much you could put in to get a saturated solution. So like sodium chloride, salt. All right, if you put 40 grams into boiling hot water, you'll be able to make a saturated solution. That is the maximum amount that you can get into 100 milliliters of water at boiling. Okay, if you go above that, you'll have solid salt now in your water. Okay, so that's what we're talking about when we're looking at a saturated solution. A dilute solution is one that is mostly water. All right. Okay, so when we're dissolving stuff down, it does make a difference whether it's an ionic compound or a covalent compound. So remember, with ionic compounds, they're made of ions, hence the name. Okay, so when you dissolve an ionic compound down into solution, it will break up into ions. All right, so like if we're looking at a beaker with water in it, we're putting some sodium chloride, some table salt in, it will break up into sodium ions and chlorine ions. All right, it will no longer be sodium chloride. All right, because of this, these are conductive. All right, you see those little extra charges on there? That makes it easier for electrons to move through the solution. All right, whereas if we were to take carbon dioxide and try and dissolve it in, okay, first it'd be more difficult because as a general trend, covalent compounds are less soluble. All right, but once you dissolve it in, it's still CO2. Okay, it's not going to break down into individual carbons and individual oxygens. You'll still have carbon dioxide. Okay, so these break down to just molecules. Okay, like if you had sugar, right? It forms chains within the sugar. If you dissolve it in, those chains will break apart, but it will still be sugar. It's not going to break down to individual carbons, hydrogens, and oxygens, because covalent bonds are just sharing those electrons. They don't actually form ions to break into. Okay, so these break into molecules, and they are non-conductive, as we saw with that ionic and covalent lab back when we were all digital. Okay, I think that's it for our vocab. Let's talk about what we're actually calculating. Okay, so if we want to know how strong a solution is, what we need to know is the molar concentration. Molar concentration is the number of moles, which is basically saying amount of stuff, number of moles per unit of volume. Okay, so if you've dissolved a lot of stuff into a small space, it will have a large molar concentration. Okay, let's look at a formula. All right, so we've got a few symbols here that we're going to be using. All right, big MC, capital M with a little subscript C on here. This is the symbol that we're going to be using for molar concentration. All right, this thing is measured in units defined by its definition. So it's your moles per unit of volume. Okay, so if we want to write down a measurement for this, like if we actually calculated a number and we wanted to say, here's what it's measured in, that would be moles per unit of volume. And usually when we're talking about volume in here, we're going to be talking about liters, moles per liter. Okay, sometimes people are lazy. Sometimes that person is me. So they don't always write mol/L. Sometimes we'll just do a capital M for our unit. Okay, so like 2 moles per liter equals 2 big M. All right, that's just a matter of laziness. Sorry. All right, most of the time I'll use moles per liter, but if you do see a big capital M there, we're talking about the same thing. All right, so the other thing, N, well, that's something we've seen before, isn't it? That would be our number of moles. How much stuff do we have? Okay, which is measured in mol, M-O-L. Very creative abbreviation. All right, and then volume is V. Volume is how much space we're taking up. Usually we're going to be measuring that in liters. Okay, so figuring out our formula, it's just the definition that we had. Molar concentration, big MC, is equal to the number of moles per unit of volume. Boom, we got a formula. Okay, so if you want to figure out your molar concentration, you're just going to take your number of moles and divide by volume. Okay, worth noting, we can move this thing around because sometimes you'll know the molar concentration. Like I've got some bottles of hydrochloric acid back there that tell me the molar concentration is 12. If I wanted to figure out how many moles are in a particular volume, like let's say that I had 1 liter of it, and I knew my molar concentration, I wanted to figure out how many moles that is, you could move this thing around. Okay, so some other versions of this formula. If I wanted to solve for number of moles, okay, well, I got to get this V to the other side. Right now it's being divided. So to cancel it out and bring it to the other side, I would multiply. Okay, so another way to find your number of moles is just by multiplying molar concentration by volume. Okay, or if you wanted to figure out how much stuff you're going to need, like how much volume you're going to need to measure out, and you know your molar concentration and you know your number of moles, you can figure out what your volume is by moving this equation around again. So getting molar concentration to the other side. Right now it's being multiplied, so to get it to the other side I would need to divide. So number of moles divided by molar concentration. Okay, so this is the main formula, all right? But you may use these other 2 versions. If you're being asked to find out how many moles you've got, you could use that one. If you're being asked to find how much volume it would take, you could use that one, okay? Algebra works in science too. Isn't that neat? Okay, let's try using it in an example. Okay, so here's our example. We're saying that we have 150 grams of salt and we dissolved it into 500 milliliters of water. We want to figure out how much molar concentration we have. How strong of a solution of salt water is this going to be? Okay, so our ultimate goal is to get to molar concentration. We've got a formula for that. All right, we've got big MC equals N over V. The issue with that though, we know what our volume is, but we don't know how many moles we have. Okay, so we can't jump straight to figuring out what our molar concentration is. If it told us how many moles we had, we could absolutely just use this immediately. Okay, but because it doesn't tell us how many moles, we're gonna have to do a little bit of work first. Okay, calculating moles, like I said, it's gonna come back. All right, so we want to calculate our moles. That's like part C. All right, we've got a formula for calculating moles. We used it a couple weeks ago even. All right, number of moles is equal to the mass of something times the molar mass. Sorry, divided by the molar mass. Lost my mind. There's our formula. Okay, now notice, we do have mass. It told us how many grams we've got, 150. This M, this molar mass right here, is not the same thing as big M with little subscript C. We use subscripts to denote different things in science. All right, so this is talking about molar concentration. This is talking about molar mass. We find molar mass on the periodic table, okay? Hey, look, that's what we need to find in B, all right? But to be able to do that, we do need to know what the chemical formula of this thing is, okay? So it's telling us we got sodium chloride. I don't see any prefixes in there. No mono, di, tri, tetra, okay? Which means it's an ion. So we're looking on our ion sheet, all right? So if you look on there, we've got sodium, which has a plus, and we've got chloride, which has a minus, okay? Now those two have the same charge. You got a positive one, you've got a negative one. Those two cancel out. If you happen to have something where it doesn't have the same charge, make sure that you're balancing your ions. If you're having trouble doing that, ask me for help. All right, so these match up, so we're gonna be left with NaCl, okay? That is our chemical formula. All right, from there, finding our molar mass, we're gonna look for our chemicals on here. So sodium has a molar mass of 23, okay? And chlorine has a molar mass of 35, okay? If on our chemical formula we had any extra numbers down at the bottom, like if we had Na2Cl or something like that, we would multiply our 23 by 2, all right? However many you have of each element, make sure that you're multiplying their molar mass by that so that you're accounting for the entire compound. All right, so we don't have that on this one. We've just got one sodium and one chlorine, so that's just gonna be 23 plus 35, and it'll give us a molar mass of 58 grams per mole. Okay. Almost done. Moles. Well, that's equal to our mass divided by our molar mass. We know what our mass is because it was told to us. We've got 150 grams, okay? So whenever you're looking at a lowercase m, you're looking at grams. That's what it's measured in. All right, so we're putting 150 where the mass was, and then our molar mass, well, we just found that. It's 58. So 150 divided by 58. I need a calculator. 150 divided by 58. Okay, so that means that we have 2.59 moles. Okay, so moles are really just describing how much stuff we have. Okay, so we have 2.59 moles. Now we can find our molar concentration. We have N, and we know what V is, but we do need to be careful. Okay, so our N, 2.59, our volume. Okay, up here it says that we're measured in milliliters. Be careful with milliliters. All right, because when we were talking about the units for molar concentration, we said moles per liter. That's in milliliters. Okay, so we need to make sure that this volume is in liters first. Okay, so in 1 liter, there are 1,000 milliliters. Okay, 1 liter equals 1,000 milliliters. So if we've got 500 milliliters, that would actually be 0.5 liters. Okay, when you're converting from milliliters to liters, here's the quick and dirty way to do it. Take your decimal point and move it 1, 2, 3 times. Okay, so our volume, not 500, 0.5. Okay, we moved our decimal place in front of the 5. All right, so from there, we're just plugging and chugging. All right, that'll end up giving us a molar concentration of 5.17 moles per liter. Okay, and that would tell you how reactive it's going to be. All right, if you've got something reacting with salt and you've got 2 solutions, one is at 5.77 moles per liter and the other one is at like 2 moles per liter, this one has more to react with. It will react more vigorously and it will react for longer. Okay, so molar concentration lets us know how much stuff is dissolved in and how reactive it will be. Okay, we're gonna have a few things on this. If you're having trouble with any of the steps getting up to here, all right, if you're having trouble finding the formula, if you're having trouble finding the molar mass or the moles, make sure that you ask me for help. Send me a message on Schoology, ask me when you're in class. Help me help you. See you later.